Hi everybody, this is section 7.2 from the Scott Stevens Think and Do Introduction to Statistics book, and this section is titled Estimating a Population Mean and Sample Size with Sigma Known. So basically this is going to be continuing on our chapter in confidence intervals, and that's really the big goal here, to learn about how to create confidence intervals. And that's really what we mean whenever we talk about estimating a population mean. We're going to estimate that with what's called a confidence interval. So here we make an estimation for a population mean based on a sample mean in the unlikely event that we know what the population standard deviation sigma is. So you see this little cross right here. That means there's a little note at the bottom of the page from the author which says it is unlikely that sigma will be known if we don't know mu. And that should make a lot of sense, right? We don't know what mu is. We're trying to estimate mu. So we do not know that. So therefore, we must not know the population data. If we knew the population data, then we wouldn't need to estimate mu. We could just calculate mu. But we don't have the population data. So the question would be, how do we have the population standard deviation if we don't have the population data? So as you can see, this is a pretty unlikely scenario. So as such, this method is seldom used in practice. However, it does provide some insight into the process and really builds the theory of confidence intervals, and it also allows us to estimate sample sizes needed for a given margin of error. All right, so here's some notation and formulas. A lot of this is review from 7.1 and earlier. Mu is the population mean, x bar is a sample mean, n is a sample size, sigma is the population standard deviation, which we're going to assume that we know here. The confidence level, typically 90, 95, or 99%. Alpha is the combined area in the two tails of the distribution. So in 7.1, we learned about basically confidence intervals for like 95%. Say we have 95% of our sample means will actually exist in this confidence interval. And these two sides right here are called our tails. And alpha is basically the combined area in the tails. Or basically, it's 1 minus the confidence level. And we express alpha as a decimal. In each of these tails, we have alpha over 2. Right? Because it's just each of these are going to be half of what alpha is. Z sub alpha over 2 is the critical value of z that basically, so z sub alpha over 2 are the z-scores that create this cutoff of our middle 95%, or 90 or 99%, whatever confidence level you're doing. So that's what a z sub alpha over 2 is basically these z-scores. And another important thing is going to be E, which is the margin of error. And that is going to be given by this formula right here. So E, our margin of error in our confidence interval, our general confidence interval, we think mu is going to be between, well, we think the sample mean is a good starting point for the population mean. Then we think it's going to be between x bar, sample mean plus some error, and the sample mean minus some error. And so this is our general form of a confidence interval for a mean. And this formula right here is how we calculate our error when sigma is known. Okay, so we're going to take our z sub alpha over 2 critical value, which we learned how to find last class in 7.1, and we're going to times that by sigma, which we apparently know, and divide sigma divided by the square root of our sample size. All right, here are some requirements here. That the sample should be a simple random sample. The value of the population standard deviation must be known, of course, to use this formula that has sigma in it. And the sample size n must be greater than or equal to 30, or the population must be normally distributed. Okay, these are basically the conditions of the central limit theorem, which is very important for distributions of sample means, which are really the foundation of confidence intervals. All right, so let's go on here to talk about calculating confidence intervals. So we know our confidence interval is going to look like this thing right up here, right? So we need a few things. Well, we're going to start with our x bar, and really we just need to find our error. And then once we find our error, we subtract it and add it from the sample mean, and those create the two endpoints of our confidence interval. So how do we calculate our E? Well, there are three parts to our E. There's the z sub alpha over 2, right? And that we need to do by analyzing our confidence level. We made a little table, and this can also be found in the back of the textbook. For each confidence level has a designated alpha over 2 for it, z sub alpha over 2. And you could also, for a different confidence level like 98%, you could create your own normal distribution like this, cut it off at 98%, and you could use that to figure out what these z sub alpha over 2 values are if you want to. All right, so once you have that z sub alpha over 2, you're going to plug it in right there into E formula. And then you're going to plug in sigma right here, plug in n right here, and just compute. And then once you compute that value, you plug that in here and here, and that's basically going to create your confidence interval for you. And then lastly, you're going to want to do step 4, which is write an understandable concluding statement. So something like, I am 95% confident that the mean, whatever your variable is, like maybe the mean IQ for all, whatever your population is, maybe like North Shore Community College students, is between whatever two values you get as your endpoints of your confidence interval. Okay, here's some round-off rules listed here by the author. When using raw data, the author suggests you round to one more decimal place than is used for than is found in the raw data. That's very similar to the rule we've been using most of the semester, so that's a very good rule to use. When you are given x bar, n, and sigma, the recommended rule is to use the same number of decimal places as for x bar. I think that's a good rule as well, because x bar was probably rounded, and it was probably rounded using the rounding rule from our first bullet point, so you can just stay consistent with that number of decimal places. And then the last bullet point says you may want to carry your margin of error out, however, to an extra decimal place or two. But remember to round your final answer according to the above rules. Okay, so when your margin of error, your E, you might want to round more than just what you're going to round your final answer to. Because that's basically like rounding in the middle of a problem, which you generally want to stay away from doing whenever possible. All right, let's move on to the next page now. Okay, so the first example on this page is a simple random sample of 35 men yields a mean pulse rate of 72.5 beats per minute. Assume the standard deviation for the population is 10.2 beats per minute. So let's first find the 95% confidence interval estimate for the mean pulse rate of all men. So some information we have here is that our sample had a mean pulse rate of 72.5. So that means that x bar is 72.5. We were also given this information, assume the standard deviation for the population is 10.2. So that tells us that sigma is 10.2. And the sample size was 35 men, so therefore n is 35. All right, so now we're trying to build this confidence interval, and the way I do is I first start by writing out my general form of a confidence interval. And that is that we think mu is between x bar minus E and x bar plus E. And then we want to find our E and then plug it into the formula. So, and I usually do my E off to the side. And in this case, we know, since sigma is known, we know that E is going to equal Z sub alpha over 2 times sigma over root n. All right, so the first thing we need to do is find our Z sub alpha over 2. And that's going to be directly related to what the confidence level was. Our confidence level was 95%. So when your confidence level is 95%, we know that the Z sub alpha over 2 that corresponds to that is 1.96. So we would plug in 1.96 for our Z sub alpha over 2. Then we plug in our sigma and divide that by root n, which is root 35. And that is going to give us our E. So we put that in our calculator machines, we crunch it up, and then we get a value back, that computation is done right here, of 3.38, and that is our E. So this is what's going to go into E in our confidence interval. And then our final confidence interval just looks like our sample mean, x bar, which was 72.5 minus 3.38, running out of room here, and 72.5 plus 3.38. So you add and subtract those two values and you get 69.12 and 75.88. And that's basically how you find a confidence interval. And you'll see the author here followed his own rounding rules, which was to the same number of decimal places that x bar was found. You'll see that rule right up here. Or is it the second one? And he simplified that to 1 decimal place. And then you would come up with a concluding statement like, I am 95% confident that the mean pulse rate for all men is between 69.1 and 75.9. All right, cool. Your turn. Try this example right here. Part B, which is finding the 99% confidence interval estimate for the mean pulse rate of all men, which comes from the same data at the beginning of example 1. So go ahead, pause the video, give it a try, and then when you resume, you can see my work and see if yours matches up. All right, so we're trying to find the 99% confidence interval for the mean pulse rate of all men. So the mean pulse rate of all men would be mu, and we think it's going to be between x bar plus some error and x bar minus some error, where we know the error is given by z sub alpha over 2 times sigma over root n. All right, so the first thing we got to find is what the z sub alpha over 2 is. And that is going to be based from what the confidence level was. The confidence level is 99%, and 99% confidence levels we found give a critical value of 2.575. You could also go 2.58 here, I guess. It's not really the end of the world. So that is our z sub alpha over 2. So our margin of error is going to be E equals z sub alpha over 2, which is 2.575, times sigma, which, let's look back, it was 10.2, divided by square root of n, which is our sample size. So what is our sample size? Well, let's go back to the data. The sample size was 35 men, so root 35. Whoops. Okay, so we would want to crunch this up. Let me put my calculator up. 2.575 times 10.2 divided by the square root of 35. Whoops, 35. And that comes out to be an E of 4.439593. I'm going to jot down a few extra decimal places here. I'll call it 4.44. Okay, so now we come up with our confidence interval, and that is just by using this general form right up here. So it's going to be, we think that mu, or not think, we are 99% confident that mu is between 72.5 plus 4.44. And 72.5 minus 4.44. So we'd want to calculate those values. 72.5 minus 4.44 is 68.06, and 72.5 plus 4.44 is 76.94. And I'm going to follow the author's rule here, which is round these to the same number of decimal places that x bar was given to us. And x bar was given to us at 1 decimal place. So I'll round these final answers to 1 decimal place. So that'd be 68.1. Oops. And 76.9. Cool. All right. So then what is my conclusion? So my concluding statement would be that I am 99% confident that the mean pulse rate for all men is between 68.1 and 76.9 beats per minute. All right, cool. So let's also take a look here at at part C, which is what happens to the size of the confidence interval as you increase the confidence level. You'll see here from parts A to part B, almost everything stayed the same except for one thing. We went from being 95% confident in part A to being 99% confident here in part B. And that was the only thing that changed. Just our confidence level went up. And what happened to our interval as the confidence level went up? Well, our first interval was 69.1 to 75.9. Really looking at this rounded version. And our second version was 68.1 to 76.9. So what happened as we increased the confidence level, as the confidence level increased, what happened was the interval got wider. So that's what we notice occurred. All right, let's move on to the next page. So the next page, page 109, is about not actually creating confidence intervals themselves, but calculating minimum sample sizes that will guarantee your confidence interval to be only so wide. Okay. So suppose you want to find the confidence interval associated with a particular confidence level, and I'm reading this bullet point right here, and a specific bound on the margin of error E. So you want your E to only be possibly so wide. We saw in our example before that as you increase the confidence level, what happened to your E? Your E got bigger. Well, suppose we want to be some level of confidence, but we don't want our E to just get bigger and bigger. We want E to be restricted to some size. Okay? Well, can you then determine the appropriate sample size? So the idea here is that you can actually keep your E from getting too big by getting a bigger sample size, because as you get a bigger sample size, you would expect your data to be more accurate, and your estimates, your sample mean, to be more accurate and closer to the true population mean. So you recall our margin of error formula here. Well, you can just do a little bit of algebra to solve that for n. And don't have the space to do it out here, but you can try it on your own. And if you do so, you get this formula right here, which is basically the minimum sample size required for a given upper bound of the margin of error, or like a maximum of the margin of error. So the sample size here does not depend on population size. So the sample size is not relative to the population size. That's not a necessary factor. It's just this formula works no matter how big the population size is. Okay, so our round-off rule here, if this formula right here, formula 7.4, does not result in a whole number, then use the next larger whole number. So basically, you're always going to round up when using this formula. You're going to round up to the next whole number. Okay? So, what if you don't know sigma for this process of getting a sample size? You could approximate the standard deviation with a formula called sigma is approximately equal to the range of your data divided by 4. Or you could use the standard deviation for a similar population if you can find one. Or you could approximate, overestimate it. Okay, so let's go on to example 2 here. A prior sample of 35 randomly selected men produced a mean pulse rate of 72.5 beats per minute with a standard deviation of 10.2 beats per minute. I want to estimate the pulse rates of male marathon runners. How many male marathon runners should I select if I want to be 90% confident that the sample mean is within 1.5 beats per minute of the population mean? So the idea here is that we want to come up with a confidence interval for marathon runners, right? Which would be different than of regular men, right? Marathon runners would probably have a lower pulse rate than regular men. So this sample right here probably wouldn't be very helpful. We'd have to do a new sample. Now, if we want to find out that sample size before we go out and collect that data, that's basically the question that we're trying to answer here. Now, I don't have sigma for male marathon runners particularly, but a good estimate could be sigma for all males. The mean we would expect to be different, but sigma, the standard deviation, still could be a potentially good estimate for male marathon runners. So then we're going to use our formula up here to get that sample size. You're going to plug in z sub alpha over 2 times sigma divided by e, and you're going to take all of that and square it. So if we're looking at 90% confidence level, we know that for that, our z sub alpha over 2 is 1.645. For sigma, we're going to use the all males, which is 10.2. And we want the sample mean to be within 1.5 beats per minute of the population mean. So that is basically giving us the margin of error, E. So we're going to plug that in for E right here. And then we just crunch out this product, quotient, square, and we get 125.1. So we're going to use the rule, which was that we always round up. And we're going to say that we should select at least 126 runners for my sample. All right, your turn, part B. How many male marathon runners should I select if I want to be 99% confident that the sample mean is within 1 beat per minute of the population mean? So go ahead, pause the video, try this on your own, and then when you press play, you can see if my answer matches yours. Okay, so we're going to use our formula again. N equals z sub alpha over 2 times sigma over E, all squared. So let's plug things in. For 99% confidence, what is our z sub alpha over 2? It is 2.575. And our sigma is still 10.2. Our margin of error here, we're looking for the sample mean to be within 1 beat per minute of the population mean. So now our E is 1. We're going to take all of this and we're going to square it. And let's crunch that out. So we get 2.575 times 10.2. And I didn't divide by 1 because we know that'll just be itself. And we're going to take that answer and we're going to square it. And we get 689.85. 689.85, which we would then round up to 690 as the next whole number. All right, so that's going to take care of section 7.2. Hopefully there were no questions. If there are, of course, come find me and ask, and I will see you in class.